Hi, my name's Graham Sexton, and I'm going to be taking you through this tutorial on link budget calculations for outdoor Wi-Fi systems. These link budget calculations are incredibly important in the commercial environment, primarily because the cost of getting it wrong when you design and build and deploy an outdoor Wi-Fi system can be very large, and also the customer doesn't like you to get it wrong, so it's really good to get it right first time. So we've got a lot of calculations to go through and considerations, and to go through this I've set a question, it reads like this. So a company, Geeks R Us, want to wirelessly connect to geographically separate buildings. These buildings are towards the center of Manhattan, New York, and United States of America, and are placed 1 kilometer apart. They do have line of sight of visibility of each other from the rooftops, but there are other high buildings all around. You're required to perform a link budget calculation to determine the deployment feasibility. You're to use Wi-Fi technology to implement the link. You need to specify the equipment and parts to implement the link. Some suggestions are given on the following pages, but you don't need to use these. You can choose others. You need to be able to show your calculations, and everything must be clear and justified. And at this point, there are a number of critical unanswered questions. The fact the questions haven't been asked and they haven't been answered, but that you would need to ask to do a real deployment. As part of the tutorial exercise, you should try, without looking at the answers, list 5 critical questions you would need to answer in addition to the ones that I've already just asked there. So in order to start the design, there are a few things that we need as an absolute minimum. We need, let me just get my pen working here. We need, first of all, the frequency of the link. So typically, at this point in time, that's likely to be 2.4 or 5 gigahertz in principle. 5 gigahertz is more popular in the United States, then you should probably think about the 5 gigahertz. 2.4 gigahertz does have some advantages. It has a range advantage compared to 5 gigahertz, but we'll need to explore that later on down the line. We need to know the path length. We're given the path length, it's 1 kilometer, and from that path length we can calculate the free space path loss, which is the biggest loss in any of the system components. We need to know the power of the transmitter. Obviously the transmitter needs to operate within regulations, especially for an outdoor link. We need to understand the receiver sensitivity. The receiver sensitivity is the lowest value, usually specified in dBms, that the receiver can usefully decode signals. Now, what you do need to be careful with there is, whilst the receiver sensitivity might quote, well, this is how low it can go and still work, it will not be working at the highest bit rate at that lowest sensitivity. And so really, in fact, it's quite hard to get at the data for most systems to tell you the receiver sensitivity to operate the highest bit rates, but you need to be operating, if you want the highest bit rates, a little bit above the receiver sensitivity value. We need to be able to specify the types of antennas that we want. If we've got a long distance link, and 1 kilometer is a fairly long distance, we need to have a directional antenna, and we need to understand the antenna gains. And we need to understand the lengths of any transmission cables that are involved, and the losses with those transmission cables, and likewise any connectors that are involved, and we need to understand the losses of those connectors. So this is the very basic stuff. Of course, there are other questions and other things that we need to know for a full deployment, but just to do a paper design, we need this information. So one of the additional bits of information that we really need is something called a system operating margin, or sometimes a safe operating margin. I've got a diagram here which shows a typical deployment of an external system, where we have a transmitter on the left hand side and a receiver on the right hand side, and we're keeping this design very simple at this point. We've got a clear line of sight between the two antennas. I've already said that there's a clear line of sight in our scenario, but we've also got no Fresnel zone encroachment as well, so that's a very important thing. So what that's saying is there are no buildings in between which might encroach into the Fresnel zone, which is a zone around these two devices. So we're assuming that Fresnel zone is not encroached upon. So the system operating margin is the difference between the receiver sensitivity and the received signal. So at the receiver end, so that's the box at the right hand side, it has a sensitivity, and we would be reading at that off the specifications of our receiver. And if we can imagine, we've got a bit of a graphical environment here where this is a scale in maybe dBms. Let's pretend there's 0 dBms up here, and let's say we've got minus 100 dBms at the bottom. Then our receiver sensitivity would be normally around about minus 90 odd, might be between minus 90 and minus 100, depends on the receiver. What we must make sure is our signal that we're transmitting when it's received is in this range up here. So it needs to be bigger than minus 100 dBms. But what we need is a system operating margin, that is a margin above the receiver sensitivity, to ensure that our system operates reliably. And the amount of margin that we have depends on the environment. If it was in a rural environment across a field or a desert or something like that, we could operate with quite a small margin of maybe 10 dBs. But in an urban environment, particularly something like Manhattan, where there might be lots of other RF sources around, we'd probably want at least 20 dBs and maybe even 30 dBs. It really just depends. So the minimum we would be looking for an SOM value would be 20 dBs in this. So if that's the receiver sensitivity value there, this margin here needs to be 20 dBs. And so this value here, whatever that is, needs to be the value that is actually being received at the receiver for it to work reliably. So we need to build that into our design, and obviously we can't do that quite yet because we don't know what the receiver sensitivity is. So one of the first things that we can do for this particular deployment is to start thinking about how the system looks. And this diagram is taken from notes you've probably seen from the lectures, and understanding where the typical losses might come in. So the big loss, and we've talked about this briefly, is the free space path loss, which is happening across this link here. So we'll be looking at how we calculate that in a moment. But there are other losses in the process, and if we have RF cables going from a bridge at one end all the way up to the antenna, they will lose power. If we have a lightning arrestor, and we'll lose power in there. So all of these things, their losses may be small, but nonetheless they're significant, and we have to take them into account. Of course, there are some gains. The antenna here and the antenna here both have gains, and we need to know and understand what those gains are, so we can include those gains in the system equations. We need to know the transmit power, and I think that's it. We've got just about everything that we need to know, at least in principle, to do the calculations. So if this was a bit more than an academic exercise, and I'm hoping that you will explore this, because if you were doing this for real, you would not have somebody probably come along and say, well, you're going to use this equipment, so basically go and plug it together. You might be doing that, but if you're doing the design work, it's more likely that you will go and have to find out what the bridges look like, or access points, whatever they are, whatever the transmission system is and receiver system is. You're going to have to find them, specify them. So you're going to need a couple of bridges. You're probably going to need some cables. You may well need some antennas, depends on the device. You may need an antenna mast. You're going to need things like pigtails and lightning arresters. So some good questions that you need to ask yourself at this point is, how would you choose that equipment? And I don't mean you'd use Google. You probably would use Google to start with, but maybe the sorts of parameters that you would use to home in on particular equipment would be, maybe one, performance. You want to make sure that the equipment you use does the job, but price will have an influence. Availability may be very important, and it may be that the manufacturer is very important. There are some customers who are very fussy about the equipment that they have installed on their premises, and it may all have to come from the same vendor, so you may be restricted. Some examples of possible components that you might take a look at, and I recommend you just clicking on those links. So we've got an example of a bridge, an example of a lightning arrestor, some cable connectors, and some antennas that you can have a look at. And it's kind of quite nice just to have a look at the specifications of these things. It's also useful to use tools that are out there. This is a link budget calculator tool, and it's fairly straightforward to use. And you might want to take a look at using those link budget calculators. What's quite nice, in my opinion, is to check your calculation with a link budget calculator. Not necessarily rely on the link budget calculator entirely. You know, there's always that danger of relying on a box to calculate your answers in case it's actually come up with a stupid answer, and you don't have a feeling that the answer is just crazy. You know, you can't go back usually to the supplier of these link budget calculators and say, hey, you got it wrong, you've cost me £500,000, give me some money. That's usually not going to happen. So you should take the responsibility of just being able to calculate that by hand, probably, and maybe use a link budget calculator just to check to make sure that you've got everything right. So the first thing that we're going to have a look at is calculating the path loss. and I'm just referring to the notes that you have been given in class to calculate the path loss. So everything really comes from the Friis equation, and I'm sure you've done a little bit of work on that and understanding what that is. Just very briefly explaining what those components are. The PR is the power received, PT is the power transmitted, GT is the gain of the transmitter antenna, GR is the gain of the receiver antenna, lambda is the wavelength of the signal, and D is the distance between the two antennas. Now, often we have a more, I say, user-friendly, but a rearrangement of that equation where we can calculate the free space path loss in dBs. So we have this equation that I'm just underlying here, which is a standard equation you can find in books and on the internet. That helps us calculate the free space path loss. It's just the path loss. It doesn't take into account the gains of the antennas. And in this arrangement of the equation, D is in kilometers and F is in gigahertz. There are other arrangements of this equation where they look essentially the same, except this number here is different, and that number varies if the units kind of vary in this free space path loss equation. So what I've done here is just to do the calculation for you. Probably it will be good for you to do this yourself, but what I've done is just to substitute the values that we know. So the first part of the equation is 20 times log of 1, where 1 is the length in kilometers, the distance in kilometers. And then I've assumed in the first case we're going to do a link at 2.4 gigs, and that gives us 100 dBs path loss. So remember that's equivalent to minus 100 dBs in the overall picture. And at 5.2 gigs, so that's one of the frequencies that might be used in the A spectrum. Everything but the frequency is the same. Frequency obviously 5.2 gigs, and our free space path loss is a little bit higher, so we've got an extra 6 dBs. In fact, 6 dBs is a lot of loss of power, really. So we're talking about 106 dBs. So we need to sort of feed that into our overall calculation. So what we've got to try and do is to put the numbers into this, and we're going to have to refer to one or two bits and pieces of other information, and what we have here is a loss of well, we've got to go for the 5.2 gigahertz, so that's approximately a loss of minus 106 to 6 dBs. Okay, now if we take a look at the example of a bridge that I have a link to earlier, and I'd recommend that you take a look at that, then what you can do is to extract from its specification sheets a number of things, and we end up with a ever so slightly different diagram potentially to the one that we have here, because the particular bridges that I have a link to have internal antennas with modest gains which you can use, but they can be connected to external antennas as well, but that's an option. So rather than having this unit here where we have a separate bridge pigtail antenna, etc., etc. We literally just have a single box which has an Ethernet connection down to our network switch in the building, and likewise at the receive end, or the other end, where we just have a single box connected Ethernet connection down. So you don't need to worry about these separate bits and pieces. Now if you inspect the that link for the antenna, you'll find one or two useful bits of information. You'll find that the power, transmit power, will be easily within the UK specifications, and let's just choose the UK specifications of transmit power, of maximum transmit power of 20 dBm. Of course, from a regulatory point of view, we might need to rein that power back a little bit. It depends on regulations at the particular point in time, and there are signs of some new regulations coming out which allow us to transmit more power on external links. The antenna gains for the internal antennas are plus 14 dBs in both cases. So that's plus 14 dBs in both cases. And our receiver sensitivity, so it's at this end, is minus 96 dBms. So essentially, that's just about all of the information that we need, and I suppose we can just first of all look at the amount of power that we need to actually receive at the bridge end. If we assume that we have a 20 dB system operating margin, then the amount of power that we need to receive at the receive end will be minus 76 dBms. So essentially that's 96 minus 96 dBms plus 20 dBms gives us minus 76 dBms. So that's the power that we actually need to receive at the receiver end. So let's just take a look about how close or far we are from being able to deliver that power. So if we start by assuming that the power output from our bridge is plus 20 dBms, and that we have a gain of 14 dBms at the transmit end, so that's a plus 14, and another plus 14 dBms at the receive end, or not dBms, dBs, these are just dBs. And we need to take into account the path loss over the link, so that's a minus 106 dBs, like that. So if we quickly add all of this up, this will tell us how much power we're effectively receiving at the other end, the receive end of a system, and that will work out to be approximately minus 52 dBms. So the big question is minus 52 dBms larger than the minimum receive power, which is minus 76 dBms? And indeed it is. It's considerably larger. So this system, using one of the bridges that I've recommended earlier, would work directly without any fancy external equipment, and that would work well. So this also gives you a margin above the system margin as well, and so you've got a good chance of the transmit system operating at one of the higher data rates as well, rather than the lower data rates. So I'd be pretty confident that this system would work, and indeed if you look through the manufacturers' data, they are pretty confident that their systems will work at considerably greater distances than 1 kilometer. I mean, that's manufacturer data, so I don't know how well it would really work, but there again, maybe it's going to 2 or 3 kilometers. I'd be pretty confident about. Going beyond that, I'd be less sure. So I think that we conclude at this point that the system is going to work, but in order to deploy it, there are a few other very important questions to ask, and these are just some of the questions that I'm kind of asking here. So probably the most important one, and I hinted this at this first point earlier on, is is there going to be any Fresnel zone encroachment? So if you're deploying antennas on high rooftops in Manhattan, even though you might have line of sight, there's a very good chance there'll be other very high rooftops around. So you'd need to go and do a survey, have a quick look around, and get an estimate of the heights of the other rooftops to see what and how the Fresnel zone might affect the performance of the system, because it can be significant. The other sort of issue is, you know, the company just said we want a wireless connection, but at this point they haven't sort of specified the sort of bandwidth that is required, and you would need to do that to be able to kind of verify, not post deployment, but to get a very good idea of what sort of bandwidth you're likely to be able to achieve across that particular link. And all of that bandwidth will be in part dependent on how much power you're going to get across to the receiver. And you know, if you're very close down to the safe system operating margin, then you might be talking about very low data rates. But if you've got, like we have, a good 20 dBs above the safe system operating margin, you're going to be absolutely fine. So you should get a good data rate. You need to have an idea of what the RF interference profile is like. That will help you design the system operating margin, and if there are many other players using 5 gigahertz for any other applications. Very practical things. It may be that you need to mount these devices or an antenna on a mast. Are there any planning restrictions for mounting antennas or masts? Are there any restrictions to actually accessing the roof on the building to install equipment? Seems like very simple stuff, but sometimes these very simple things can be the hardest things to overcome if there are building restrictions. And another one is, how can we route any cables that are required from the office machine room to the roof? And again, it sounds like a simple one, but you know, this sort of thing can be an absolute nightmare, and indeed cable routing can be one of the most expensive parts of the whole exercise. So that brings me to a conclusion for this short video. I hope that's been a little bit helpful. I'd encourage you to have a look at the specification of some of those devices, and just try a few of those different devices with slightly different configurations yourself, just to see if you get reasonable answers. So thanks very much for watching.